Hello, and thank you for attending my presentation today where I will be sharing with you my work studying the fast transport of ultracold atoms, and in particular, the effects of STA protocols and counterdiabatic driving on post-transport fidelity. Obviously, feel free to pause this video and read if you're watching this on your own, but if this is being presented in my absence instead, I should let you know that I will not be reading directly from the slides, but instead describing the content in alternative wording. So it may serve you better to either read or listen, but not necessarily both. With that being said, let's begin. But first, a little bit about me. My name is Chris Larson, and I'm currently an undergraduate at Miami University. I'm a physics major and math minor, although after graduation, I do plan on pursuing my doctorate degree. I'm particularly interested in studying quantum field theories and the Standard Model. More specifically, I would like to study nuclear and particle physics. Now then, what is it that we actually do here? Well, in our lab, we simulate the time evolution of trapped Bose-Einstein condensates, or BECs, within a moving painted potential. We have control over a range of parameters from the size and shape of our trap to the atom count in our BEC, but primarily we're interested in comparing post-transport fidelities of BECs following two different trajectories from its initial to its final position. Why is our work important? Well, primarily, our research pertains to the field of atomtronics, where work is currently being done to develop atomic analogs of many common electronic components, such as diodes or transistors, using trapped ultracold atoms instead of electronic circuits. Some components have a range of potential applications in ongoing research fields, such as atomic optics, quantum computing, or gravimetry. Currently, however, one of the many dominant obstacles to building atomic or atomtronic devices comes from the difficulty in creating BECs as well as maintaining their coherence or the coherence of the wave function through transport without the use of large, bulky, lab-based setups. So how exactly do we simulate transport? Let me start by introducing the Gross-Pitevsky equation, as you see on the left. This equation is a nonlinear modification of the well-known Schrödinger equation, one which adds a nonlinear potential term proportional to the density of the wave function by a proportionality constant g. This term represents the repulsive forces between different atoms within the BEC, as the raised potential in high atom-dense regions drives atoms away from each other. Now, as mentioned before, the goal of our work here is to compare post-transport fidelity of BECs following two different trajectories, those following shortcut-to-adiabaticity, or STA protocols, and those following constant acceleration for the first half, followed by constant deceleration of equal magnitude for the second half. The difference between these two trajectories is that in STA transport, motion is further smoothed by the addition of two higher-order terms, a quartic and a quintic, which aim to not just make position continuous and smooth, but the acceleration as well, which is important later in applying counterdiabatic driving in suppressing undesired excitations to the BEC with motion. As you can see here, the blue line denotes STA transport and spans the same distance and the same time as the acceleration-deceleration path in red. Although where the former becomes piecewise in its higher derivatives, STA transport remains both continuous and smooth, all the way up to acceleration. In addition to this slightly varied trajectory, another important aspect of STA protocol is the counterdiabatic driving through the application of an auxiliary potential in addition to our trap. This potential is described by the following equation and linearly decreases the potential in the direction of and proportional to the acceleration of the trap. On the right, we see an example of this in how the blue line, representing a trap following STA protocols, leans forwards during acceleration and backwards as it comes to a halt, as opposed to the red line, which simply follows constant acceleration and deceleration motion, without a corresponding auxiliary potential. Towards the beginning and end of transport, the slight difference in the trajectories can also be seen in the slight momentary offset of the traps from one another. In order to contain the BEC through transport, we need to model a trap for our atoms. To do this, we add together the potentials of three beams, one along each axis. This sort of trap is referred to as a painted potential and is easily realized in a laboratory setting. Along the axis of motion, designated the x-axis, our beam forms a simple circular Gaussian. Along the two other axes, we draw a scanned Gaussian to elongate the trap, which approximates a constant potential where the beams scan with constant speed. But they follow a nearly Gaussian shape at the edges, with the shallowness of the slope corresponding to the width of the beam. With a sharper, more precise beam, we can create sharper edges and correspondingly increase the effective trap frequency. As you can see on the bottom right, close to the center of the trap, equipotentials approximate ellipses. Also shown is how the auxiliary potential in STA transport perturbs our trap, dividing space between the high energy region on the left and low energy region on the right, separated by the planar isosurface perpendicular to the axis of motion. Here, I have a small selection of animations for transport following each trajectory over a range of varying transport times. Note that these isosurfaces no longer represent equipotentials of the trap, but are instead representative of constant wave function amplitude, so we can view how varying transports affect the BEC itself. For acceleration-deceleration motion, in just a quick 5 milliseconds, the BEC does not leave its initial position and is instead stretched out or spilled as the trap moves so rapidly that it leaves the BEC behind. Compare this to the STA trial, which despite being distorted by the end, at least remains inside the trap through transport due to the aid of the auxiliary potential. With slightly lower speed, now spanning the same distance in 15 milliseconds, we see that the BEC following accel-decel motion does actually make it to the end of transport, but with a significant amount of sloshing, destroying the ground state. With STA, sloshing is significantly reduced through transport, although there is still somewhat of an impact upon stopping. For slowest motion, over 30 milliseconds, sorry about that, whoops, we see accel-decel motion with only slight distortions during transport, although upon coming to a halt, the BEC can be seen rippling back through itself, not dissimilar to the jerk of a car coming to a halt in front of a stop sign. In STA, even this excitation is eliminated as the final state of the BEC matches its initial ground state with significantly higher fidelity. As mentioned before, we have control over various factors of transport. These include the beam width for the scanned Gaussian, the trap depth, and the trap length, as well as the number of atoms, transport distance, transport time, and of course, the trajectory of motion. Getting into the actual simulations now, I figured now would be an appropriate time to mention that when actually calculating the fidelity of the BEC post-transport, one thing to keep track of in the results is that due to the non-zero ground state energy of the BEC, there is a phase shift with time to the corresponding wave function, as can be seen on the right. To measure the instantaneous fidelity post-transport without taking this into effect risks catching the BEC out of phase with its initial state, despite being an equivalent ground state under global phase invariance. If this frequency were consistent through transport, one could simply phase shift the ground state for comparison at the end. But throughout transport, especially in accel-decel motion, temporary excitations can cause a range of these frequencies, so there is an overall phase shift by the end of transport, despite the appearance of ending close to the same frequency. To account for this in the data, we let the BEC sit stationary in the trap post-transport after it's come to a halt, and measure the fidelity over time for the next 7.5 milliseconds. We then take this time average fidelity over this interval and take those to be the post-transport fidelities seen on the following slides. Note that, as a result, the following fidelities are actually lower than their true value. For example, while the actual fidelity of this plot maximizes at over 90% by the end, the measured average fidelity would sit a little bit under 80. With these plots, we compare post-transport fidelity against increasing transport time, otherwise thought of as decreasing speed, for acceleration-deceleration transport on top and STA transport on the bottom. The left two plots show a smaller BEC of just 2,000 atoms, while the right side shows fidelities for 50,000 atoms. The various colored lines on each plot are representative of increasing trap depths, or correspondingly trap frequencies. What we see is that for any given line on the top two plots, fidelity initially seems to increase as we reduce the speed of transport, but at certain transport times, the fidelity falls off again before recovering. The timing of this dip seems to shift left consistently with increasing trap frequency as well. One possible explanation for this would be that these dips represent intervals where some sort of resonance is reached between the change in applied force halfway through transport and the frequency of the trap, or the oscillation of the BEC within the trap based on that trap's frequency. On the following slides, we will further investigate this. Assuming this to be true, though, what is seen by the bottom graphs is that analogous transport under STA protocols shows resistance to excitations caused by resonance within the trap. This finding is significant because it shows that STA protocols can reduce or even eliminate the adverse effects of varying trap frequency on post-transport fidelity, reducing several degrees of freedom from consideration in an experimental setting, such as trap depth, length, width, or any other factors affecting frequency. Now, comparing atom number, we see that with an increase in atom number from the left graphs to the right, the average fidelity post-transport is raised in both acceleration-deceleration motion and that following STA protocol. We have two ideas that could explain this. First, it could be the result of some balancing act between the repulsive forces inside the BEC and the restorative forces of the trap, where leaving the trap mostly empty could be resulting in larger oscillations of the BEC with motion. If this is the case, more work would need to be done to find the optimal trap size for a given number of atoms, so that the trap is not too loose to hold the atom still, but not too large as to overfill it. This idea hinges on the relationship between the spatial oscillation of the BEC based on a combination of both the trap frequency and the strength of interatomic interactions. Secondly, this could also be an artifact of how we actually calculate the fidelity, as described previously. This idea revolves around what fraction of the overall BEC is temporarily excited through transport, and what remains out of phase compared to the rest of the BEC when returning to rest. Note that these two ideas are not exclusive to each other, and both could easily be factors. Returning to the topic of resonance, we now wish to explore these dips in fidelity present in the acceleration-deceleration plots. In the second column on the table to the right, we list the closest time intervals to each point on the dip for the various trap depths tested. If you wish, you can verify that these numbers align with the plot below on the far right. Next, we wish to calculate the trap frequency for each of these trap depths and compare. To do this, we can take our BEC in each of these stationary traps and give it a small kick. From here, we track the variance of the wavefunction with time as it oscillates in the trap. Performing a simple Fourier analysis of this variance yields the plot shown on the far left, with a distinct peak at the dominant trap frequency, and with smaller peaks appearing occasionally as harmonics. Taking the dominant frequency over a range of trap depths yields the next plot to the right, which, converted to corresponding periods, gives us our third plot. These periods are now listed in the third column on the table for comparison. And what we see is that the dips in fidelity seen before do align with odd multiples of the trap frequency, which is what we would expect to see if resonance is the cause for these dips. Also expected would be the appearance of more dips at higher modes, although to a lesser degree due to the reduced speed and applied force through the midpoint for these longer transport times. Looking at the 50,000 atom XL-decel plot again on the next slide, these higher modes are present at the expected positions as well. Overall, STA protocol shows potential for its application in BEC transport due to its efficiency in suppressing trap resonance with motion. This helps to achieve higher fidelity transport at faster speeds and with more consistency. This could be of particular interest to experiment due to the reduced degrees of freedom resulting from a trap frequency independent post-transport fidelity. Additionally, future work could be done here to investigate the connection between atom number and average post-transport fidelity, potentially eliminating more parameters from consideration. Finally, I would like to recognize several people and organizations for making this research possible. I thank the Miami Dean Scholars Fund and the Undergraduate Summer Scholars Program for funding my research, as well as the Parent Fund and Garland Professorship Fund for funding my trip here to Chicago. I would also like to thank Dr. Jens Mueller for his invaluable help managing the Red Hawk supercluster, on which these simulations were run, as well as the cluster itself. Finally, I owe much of this to the previous members of this lab, from which I inherited the 1D and 2D versions of this code, and those would be Skylar Wright and Denuan Vithanaj. I apologize if I mispronounced that.